Hi everyone. So let's get started with our lecture number 3. So this week we're going to be covering a little bit of more on polyhedral sets, but now we're going to look at them into this what is called the standard form of polyhedrons, um, which basically means that we're going to look into them as being described by a collection of equalities instead of inequalities. Um, and we'll see how this connects with the notion that we saw last class in terms of bases and basic solutions and so on. Then we're gonna look into the definition or the consequences of having redundancy, which kind of correlates with that standing assumption we've been having of having linear independence of the columns of a matrix. So basically, we'll look into the case of what happens when it's not the case and what we can do about it. Then we're gonna start looking into developing the conditions that the algebraic conditions we can check that allows us to figure out whether a solution is optimal or not into an algebraic setting, because that is gonna be basically the underlying mechanism of the algorithm we're gonna develop next week, which is the simplex method. And then we'll put it all together in a sort of a prototypical algorithm, just paving the way to actually having a look of the mechanisms behind the simplex method. Even though by the end of today's class, we'll probably have seen most of what we need in terms of devising the algorithm. So this first video is about this notion of polyhedral sets in standard form. So let's get started. Um, so LPs so this is sort of a kind of a nomenclature that sometimes it cannot sometimes it might not be as consistent when you look at different references. Sometimes you might see the word canonical being used as well. And sometimes they kind of mean different things, but they mean the same thing, or sometimes they mean similar things, but in a different order. What I'm trying to say is that sometimes what people say is that um, you presume that your problem is in a specific form, for example, with only less or equal than constraints, or greater than equal than constraints, and minimizing or maximizing, um, and call that a standard or a canonical form. And given the name it's given for the first, this, which is the version of the problem in which you only have equality constraints, then become either the standard or the canonical. So basically, in our course, whenever we say standard form, we mean the problems that have equality constraints. Um, so and we'll talk briefly about how you can turn inequality-based problem into an equality-based problem. So basically, any polyhedral set with inequalities can be written with an equivalent by an equivalent polyhedron using equality constraints only. Um, and that for us is going to be standard form, and we'll leave the word canonical to denote this kind of format we presume our model is when we feed into the simplex method. In our case, can be, for example, maximizing with less or equal than constraints only. Okay, all right. But so for the sake of understanding what the standard form is, we look at this polyhedral set, which is basically given by a collection of constraints that are represented by equalities, and then a requirement that all variables are non-negative. And then we assume that m of these equality constraints are linearly independent. So m, because A is a m by n matrix, we are assuming that A is full row rank. Okay, so it has as a rank the same number of rows. We saw from last time, but that's kind of something, correlating it with the notion of standard polyhedrals. So a basic solution is obtained if you are in Rn, is obtained whenever you cross any hyperplanes or whenever you have n constraints that are active. So if you are in R2, you need two constraints to intercept, so you form a point. And we saw last time that a point, a vertex, can be represented by a basis in that space. If you have a 3, then you need 3 and 3 and so on and so forth. Okay, so we know that whenever we're thinking about a problem represented in a standard form, you are given from the get-go m constraints that are active. And the reason for that is because they are equality constraints, which is the very definition of active constraints. So you always satisfying equality constraints at the hyperplane, at the boundary, right? Because you're not defining a half space, you're just defining a hyperplane. So you already have m of them. Um, so to form an actual basic solution to have the intercept of n active constraints, well, we have to go around and make the remaining the difference between total n minus the m constraints you have to make more constraints active. So what do we do? Well, we turn our focus to these constraints. So if our problem is in Rn, you have n of those. And what we're trying, what we want to do is to, from these n constraints, we'll pick n minus m and make them active. Because then we will achieve n active constraints that would then form a vertex for us. The question is, how do you do that? Well, if you pick these constraints and make them active, what you are making, what you are causing in practice is to make your these variables, the variables for which you pick the constraints, they're gonna have a 0 value associated with them, because the constraint greater or equal than 0 being active means equals 0, right? So with that, so with the combination of looking at these m constraints that are active and picking these n minus m other constraints so that you form n active constraints, you will obtain a basic feasible solution, right? At presuming that all the others satisfy the non-negativity conditions. Okay. So that's kind of what is behind what we're going to see in this theorem 1, so that you can just choose n minus m variables to be set to 0, forms a basic solution. And the theorem has this form here as presented in theorem 1. So basically theorem 1 is showing this relationship between, because you're picking linearly independent columns, then you forming and then you adding the 0 variables, you basically forming a basis. So let's go. It considers, like, it looks like this. So you have your m constraints ax equals b and your non-negativity constraints, and let us assume that A has m linear independent rows that I'm just naming them like so. This is the same as saying that it has full row rank, by the way. We saw that in the last couple classes. So if I pick x bar, which is a given vector, we say that it's a basic solution if we have that the constraints are satisfied. So the problem is feasible for these constraints, and that means that we have already m constraints. And what we have is that there exists indices representing by b1 up to bm. So these indices are basically saying that I'm picking columns of A, where I have originally n columns, and from the n columns I'm picking m columns. So, and I'm doing that in a way that the columns are linear independent as well. And if it is such that I have a column for which it's not represented by those I selected, then the respective variable is set to 0. So basically what this is saying, we'll see this picture quite a few times, but I look at A, so this is my matrix A that has my columns like so, right? So that could be A1, that could be all the way to AN. And then I'm selecting, say, this. So B1 is 1. Suppose I'm getting another one here that is B, I don't know, B2 is I don't know, n minus 1. Okay, so I'm picking columns. And then what we're saying is that all the other columns that I don't select, so I select n of those, sorry, m of those, And the other ones that I don't select, I make the respective variable that is associated with that column. Remember that we have a vector, xj, x x1 all the way to xn here. So the respective component that will be associated with that column, I'll make that component 0. Okay. And that will form us a basic solution. The way to prove that, I'm not going to give explicit proof for this, but it is it's very straightforward with what we have seen from the previous lecture. So basically, you go back and look at Theorem 4. So Theorem 4 is the one that is relating the notion of spanning of vectors that is span a space being linear independent and forming a basis. So that's you need Theorem 4 to combine with the notion that you assuming that M are linear independent rows, and then you can use Theorem 14 because it's in the proof of Theorem 14, which is the one connecting extreme points, vertices, and basic feasible solutions. You can see that you can use that to the linear independence can be used to show that it's an extreme point, and then you have a connector that takes you all the way to a basic feasible solution. So have a look at that, at these two theorems, and you hopefully can see that it's basically just picking parts of these two theorems. And so when you set, by the way, when you set n minus m variables to 0, what we're also doing, it's equivalent to the same. It's kind of like a simultaneous effect, if you wish, is that because you have a system with m equations and n variables, remember that n is greater than m by definition. So basically, what you're doing is you're leaving m variables for m equations, and then it becomes a uniquely determined system given that the m rows are linearly independent. So this is what we're seeing here. So if I look at when I look at the system formed by only those variables that have not been zeroed and their respective columns, because the remaining variables have been zeroed, I can, make this look like so. So I'm including here all the variables, including those for which I set x to 0. And that is just the original form, which equals b. So that means that as soon as you set n minus m variables equal to 0, this becomes a uniquely determined system because you have exactly m equations and m variables. Okay, and that's actually the system you solve to find what is the vertex that you're referring to when you make a selection of these elements, right? So that's exactly what we're talking about here. So with this in mind, we basically have a mechanism, a method, if you wish, to form basic solutions, and we can basically construct all of them. I look at my matrix A, and from my matrix A, what I have to do is to choose m columns, and these m columns are what gonna compose my system of equations, right? A given system of equations. Once I pick these m columns, what I can do next is all other variables that are not represented by the indices of the columns I chose, make them 0. Okay? Once I do that, I'm basically forming a basic solution, because that means the last thing I have to do is to solve the system AXB to obtain the value of the variables that have not been zeroed, right? So again, I have a numerical example coming right up that we can analyze this in more detail, but just to revise, to make sure this is clear. So from my n columns, I pick m of them, and these m columns will represent those variables forming that will form my basic solution. What I do then is to, in order to make sure to calculate those variables, the value of those variables, I set the other variables to be 0. The variables that haven't been selected in those. And once I have this, I can solve the system to obtain the value for these variables. So basically what you're looking into is, right, given my equations, right, given the equations of your system, what are the other points I have to set to 0, or the other variables I have to set to 0, such that I have enough active constraints that would intersect and form a vertex. And the way it's constructed is such that you always have n equations being intersected, being crossing each other. So that means that you always have n active constraints forming therefore a vertex. Okay. So here is so we say that a solution, if the solution is such that everyone is non-negative, all the variables that for those you found the values are non-negative, then that's not only a basic solution, but is also a basic feasible solution. Okay, so let's just look at some sort of nomenclature that is going to follow us for the next, I don't know, 100 years, I guess. So the first of them is this notion of a basis. Okay. In linear programming in general, when we say we have a basis, this is kind of an overloaded sort of meaning, because we're saying that when we say we have a basis, is not only a collection of vectors. A basis in linear programming is basically a collection of columns of your original matrix A and their respective indices. So you look at your matrix A and suppose you pick columns 2, 4, and 6. So this B, the basic matrix, which is sometimes we just refer to as a basis, is the column 2, 4, and 6 of the matrix A. And we also have the basic indices, which we're going to represent by this capital AB in set. And these would just be a set of indices. So it would be 2, 4, and 6. Okay, and that's a basis. And once we have a basis, obviously we get the notion of a basic variable. So a basic variable is a variable that is selected in the basis. So it's a variable with the index that is in the set. And if you have a basic variable, you also have a non-basic variable. So a non-basic variable is simply the variable that is not selected to be in the basis. So it's gonna be those variables for which you're gonna have the value set to 0. And it's basically the collection of the variables set minus, so this is the set difference minus the indices of the basic variables. So in our, suppose our original problem had, I don't know, 7 variables, and just for the sake of the example, we picked 2, 4, and 6. So 1, 3, 5, and 7 would be our non-basic variables. Okay, again, we'll have a numerical example shortly so we can make this a bit more concrete. And that's kind of what's going to drive our development from now on, this notion of having basic variables and non-basic variables. So just a quick remark before we're looking into an example is that because it's a premise that the columns are linearly independent, the underlying system of equations that you are left with when you set your non-basic variables to 0 is always possible to be solved because B is invertible. And remember Theorem 1 that you had a collection of equivalent statements, and one of them was if the columns are linearly independent, then it's invertible. Okay, so for xb looking like so xb is just the part of x that is related to the basic variables. So it's kind of like I'm filtering the vector x and only keeping the basic indices. And by the way, sometimes when I have to write column vectors in lines, I use these parentheses. So this is a column vector, okay, for xb. So this and this are equivalent. Just a notation detail. So the unique solution for this system that we are left with can be simply trivially calculated like so. Right? By the way, in Julia, just like in MATLAB, you have something that is called the backslash operator. So you can calculate these things by doing something like so. Inf b times b, the vector b. But inversions are not exactly efficient operations. So a more efficient way of finding these solution for these systems is to actually use xb equals b backslash b. So this thing here is called the backslash operator, and it's basically an overloaded operator that has lots of matrix decomposition methods built in. And basically what it does is try to infer from the structure of the matrix B what would be the best decomposition method to be used to find the solution for X, which ultimately means doing this, but actually without really having to do inversions. So it's more efficient in terms of computational operations. So the backslash operator, and in Julia you can just type b backslash less b, and then you get the value of xb. Okay, we'll do some exercises on that as well, but just an important remark, because this is actually the operation upon which everything in terms of linear optimization is based upon. And if this is not efficient, everything else that we build upon is not. So the really kingpin of linear optimization, the thing that if you pull everything else falls apart, is this operation, which I find quite fun and quite interesting in the context of optimization. So that's the very core of what we're doing. Anyway, here is our numerical example. So here is so basically this is a system of 1, 2, 3, 4, 5, 6, 7 variables and 1, 2, 3, 4, 5 constraints, right? So basically, in order to find a basis for this, what I have to do is to select 3 of these columns and make them 0. Because once I make 3 of the columns 0, I get a system of 4 equations and 4 variables, and it's solvable. And when I solve it, I get a solution for X, and a basic solution for the system. So let's have a look. I have one example here is that I made a selection of variables 4, 5, 6, and 7. So just to clarify the notation from before, B1 would be equals 4, B2 would be equals 5, B3 would be equals 6, and B4 will be equals 7, and N is 7, M is 4. So I have to select N minus M equals 3 variables to make 0, so make other 3 constraints active. And because this is a thing in R7, because I have 7 variables, I need 7 hyperplanes to intercept, so I have a vertex, which is a basic solution. And that's Theorem 14 of lecture 2. All right. So in this case, what we'll do is that I select those as being bases. So that means that because I'm doing 4, 5, 6, 7, I'm saying that 1, 2, and 3 are 0. Okay? Because 1, 2, and 3 is 0, then when I go solving the system, notice that I end up with a identity matrix. And that's something that is going to pop up quite often, by the way. We'll go back to this when we talk about how do you convert inequality problems into equality problems. Whenever you do so, you always end up with kind of a basis like so. Identity matrix. And that's good for us because, the inverse of identity is the identity. So when I do this, it turns out that my XB is exactly 8, 12, 4, and 6. 8, 12, 4, and 6. So this is my XB, my basic variables. My non-basic variables being 1, 2, and 3. I set them to 0. So when I look at the whole vector X, I get 0, 0, 0, 8, 12, 4, and 6. And that's my basic solution, which is also feasible because everyone satisfies non-negativity conditions. So I'm good. If I do another selection, I think 3, 5, 6, 7 I chose. Yeah. So if I do 3, 5, 6, 7, I can do the same process. I'm picking this column, this column, this column, and this column. Then I need the backslash operator because the inverse is not as obvious. If you go on Julia, type that basic variable, that basic matrix 1, this column, this column, this column, this column. Do a backslash operator, you'll find a value of XB like so, which is a basic solution, but it's not a basic feasible solution because that point is crossing when x2 is sorry, x5 is negative. So we can't accept that. So it's a basic but not a basic feasible solution. It's not BFS. So that's the connection between basic solutions and problems written as in the standard form. All right. So one thing that it's relevant for us in this context is to look at the notion of adjacent basic solutions. I think we briefly mentioned them before, but here I'm putting a formal definition. So basically, you will say that two solutions are adjacent if they are connected by a line. That's kind of the geometric definition of that. But two alternative ways of saying so is that if they share n minus 1 linear independent active constraints. So if you look at two bases, two vertices, they will say that they are adjacent if they share at least, if they share exactly, n minus 1 active constraints. So the difference between the two is that one has a constraint that is active that the other doesn't, and vice versa. Another way of saying so is that if it's B1 and B2, now it's a kind of a column view. If all but one column forming the system is the same. So we just actually had an example of adjacent bases, right? When we had 4, 5, 6, 7, and then we had 3, 5, 6, 7. So 3 and 4 is just one. So they are two, they are adjacent to each other. So which is exactly what comes in here. So yeah, so the base is 4, 5, 6, 7, which is formed by these, and the base is 3, 5, 6, 7, which is formed by this, and then these three. They are adjacent. The notion of adjacency, you can also think like this sort of collecting one using a line connecting them two. It's basically, you can kind of see that when you go from here to here, you're making the variable 4. When you came in this direction, you made variable 4 0, and then variable 3 took value, right? So basically what you are allowing for is for one dimension to leave 0, while another dimension goes to 0. So this is equivalent if you look at a polyhedron set like so. So you have these two vertices here. So the difference between these two, so at this point, you have this constraint and this constraint intercepting here. This vertex and this vertex, they share this constraint. And because this is R2, they can only have one different. And the one different is that here and here they are different. So it's almost like saying that you're allowing this lack of this constraint be different than 0, so you're not sitting in that, while making this lack of this constraint become 0. And by doing so, what you're actually doing is walking on this line. Hence the phrase adjacent, because you are literally walking on a line connecting them two. And it's always a line regardless of the space you are, because you're doing one variable only. So it's always one dimension, and this is always a line, regardless of the dimensionality of your space. All right. That's exactly that's the remark right there. Okay. Right. And the last thing before we wrap up this part is this full rank assumption. So basically, we always saying this thing that we assume that our matrix A has full row rank. So the rows are linearly independent. And the question you might ask yourself at this point is, what happens if not? What happens if one of my rows is actually linearly independent? Well, the mathematician answer for this is nothing. It makes no difference. And that's exactly what Theorem 3 is about to show. That it makes no difference. If you have a linear independent row, the polyhedron you're forming, the polyhedral set you're forming is exactly the same you would if that line wouldn't be there. Right? So it doesn't matter. The engineering answer to that is, then you have a problem, because if you don't have linear independence in your rows, your matrix B, when you select the columns, is not going to be invertible. And if it's not invertible, you cannot solve the system for XB. So you actually, if you try that and you use your backslash operator in St. Julia, you get an error. It says, I can't calculate this system because these are linearly dependent. So one good practice is, before you go solving a linear system, look at your matrix and calculate the rank of it. And see if somehow, if the rank is less than the number of rows, well, your B matrix is going to be square, right? So if the rank of your matrix is less than the number of rows and columns you have a problem, because you had a redundant constraint, a constraint that is not doing anything there because it's just being a combination of the other constraints and defining the same polyhedral set. This theorem 3 is showing you how you can see that it's actually defining the same polyhedral set. So let's have a look. By the way, I said you can calculate the rank of the matrix. In Julia, you just, using the linear algebra package, you will have a function rank. And in MATLAB, you also have a function rank. And most of the respectful programming languages used for scientific computing will have a rank calculation. So let's have a look at this notion of redundant constraints then. So let P be just this polyhedral set defined in standard form, where our matrix A is an n by n matrix with rows represented like so. So I'm representing the rows with lowercase. Normally I use lowercase for the rows and capital letters for the columns. And I have m rows. And I'm assuming that the rank of my matrix A is less than m. So that means that my rows, they are not linearly independent. I only have k linearly independent rows, not m. So some of them are linearly dependent to the others. But the rows k, and I can find rows, k rows that are linearly independent. Then, and that's the catch, the set P, the polyhedral set P, is the same set as the polyhedral set Q, which is given by only those k linearly independent rows. So that's the mathematician way of looking at that. It doesn't matter because it's the same. So how do you see that? So basically 3 steps. So because it's more of a simpler proof, I decided to put in the lecture because also gives you a bit some practice of looking into these proofs, and they're going to be part at this couple weeks in our course as well. So so let's assume without loss of generality that I just have it so that I got lucky and my first k rows are the ones that are linearly independent. Of course, this is without loss of generality. I know that P is a subset of Q, and that's a given. And it's simply because Q is defined by less constraints than P. So if you're satisfying the constraints in P, you're satisfying the constraints in Q, because Q is just a subset of constraints in P. So this is easy to prove. You can just reason. The next thing is to think that because your rank is K, these form a basis, right? The K rows I selected, which I could actually, now I'm thinking, I could have just say A1 to AK because I've made this assumption, but I don't know why I did this and did that. Never mind. But yeah, so I picked those K rows that are linearly independent. So because they form a basis in the row space of A, any other row I have, I can represent as a linear combination. We saw that in the last couple weeks. Any of those rows of M can be represented by a linear combination of a basis, of the rows that form a basis in the row space of this matrix. So I have K rows that are linearly independent. My rank is K, so my dimension of my row space is K, and I have no basis for that, so I can write that. I can write that row because it's linearly dependent, right? That being the case, then I can pull a little trick just to observe the following. So let's get a point Y that lives in Q. I'm assuming that it lives in Q. And I'm looking at a constraint I of the matrix. Okay, and what we just said is because y is in Q, it means that it satisfy this. Sorry, it satisfy this. So I can use those as a basis, and because of what we just seen before, I can write any row of M, any of these M rows, which are originally for the original whole matrix, as a linear combination, right? So from this, I go to this. And I know that this will be the case as well, because that's coming from that. And likewise, I can write a combination to get me BI. So when I look at this and I look at this, I just reached the conclusion that Y also belongs to P. So basically we started proving that P was, so if this is my set P is contained within my set Q. And in the second half, we just showed that Q is inside my set P. If these two things have to hold simultaneously, what that means is that Q has to be identical to P. And that's the conclusion we reach right here. And the reason for that is actually more simple. It's simpler than it might look at first, really. It's basically telling you the following. If you have, let me see if I can find, yeah, I have some here. Basically what we can see is if you have a set, say, formed by these two constraints, like so, and you're adding a third constraint here, which is, say, the addition of these two, this constraint is redundant. Satisfying all these three constraints simultaneously is still satisfying being in this feasibility set. Let's assume that this wants everything that is in this direction and everything that is in that direction. So with or without this constraint, the feasibility set is still this, the polyhedral set formed. So that's kind of what that theorem says. If it is indeed redundant, it doesn't matter. And by the way, your professional solvers out there and open source solvers as well, they have this thing that is called pre-processing, which is basically a way to look into a problem and mine for provably redundant constraints that can be removed from the get-go. So here is a small example that you can try out to see the consequences of having redundant constraints. So basically, if you try to solve this system as if, so you see that this system has 3 variables and 3 constraints, so you don't need to find any, there's no basic variable to set to 0, right? So you can make all the variables basic. But if you try to solve this with backslash operator, you're gonna get an error. And the reason for that is because this column, or even this row, it's the addition of these 2 rows. So what you actually have to do is pick one of those, perhaps this, get rid of it, and now you have a system with 2 equations and 3 variables, and then you need one basic variable to form basis for this, and you end up with the equivalent polyhedron. You're going to be describing exactly the same polyhedron. Okay. All right. So this is just, to clarify why we keep assuming that you have row rank being n, and what will happen if it's not. So in a mathematical sense, nothing. You're doing the same thing. But in an engineering sense, there is a really important practical consequence that it might mess up the way you're calculating your basis. All right. Let's have a break here. I think the video is pretty long already, and then we'll carry on in the next part talking about the notion of degeneracy, and then moving along to the other parts of the lecture as well. So yeah, so see you in the next video.